This is lesson 12 of the chemical bonding storyline, the final lesson. The chemical bonding storyline titled, Why Do Some Things Get Colder or Hotter When They React? The first half of this bonding storyline covered 7 lessons, which took roughly 15 class periods to teach, and I taught these lessons during marking periods 1 and 2 of the high school chemistry curriculum. Whereas the first half of this storyline focused on an endothermic reaction, the second half of the bonding storyline focused on an exothermic reaction, and these 5 lessons were nicely connected to each other. As the first half, the second half also took roughly 15 class periods to teach, and I taught these 5 lessons during the second half of quarter 2 and quarter 3. This means that this entire storyline can be taught during the first 3 quarters, encompassing roughly 1 class cell per week, if this is how you choose to organize it. Lesson 12 is titled, Can we predict whether a chemical reaction will be either exothermic or endothermic? This final lesson takes roughly 2 class periods, and again, I taught this during the very end of the 3rd marking period. Lesson 12 nicely follows lesson 11 because it builds on the energy diagrams, namely the exothermic versus the endothermic potential energy diagrams. To start off lesson 12, I bring students back to one particular exothermic reaction that was very memorable, which is the combustion of magnesium ribbon, as shown in this GIF animation. In order to make this reaction happen, reactant chemical bonds need to be broken, which requires an input of energy. Once these reactant bonds are broken, a transition state is reached, and new, stronger bonds can be formed, which result in the concomitant energy release, as signified by the larger blowtorches. Now, at this point, the students have already learned that there's a relationship between kinetic energy and potential energy. But to make sure that they fully comprehend it, to draw a connection between kinetic energy and bond energy, I asked them to draw these diagrams in Pear Deck so that I can make sure that every student has reached the same point at this very final lesson. Students should know that magnesium combustion is exothermic, so they should be able to draw that exothermic potential energy diagram. But can they now also plot the strength of the respective reactant and product bonds? As you notice in this chemical potential energy diagram, the potential energy of the products are much lower than the potential energy of the reactants because the strength of the product bonds are so much greater than the strength of the reactant bonds, as emphasized by the bicep curl. Students now get a second chance to show that they really understood all these concepts by now drawing an endothermic potential energy diagram, as shown by this very first reaction of the chemical bonding storyline. For the endothermic reaction, the potential energy of the products is much higher than the potential energy of the reactants. This means that the strength of the product bonds are weaker than the strength of the reactant bonds. So the strength of the bond is dropping comparing the reactants to the products, whereas the strength of the bonds is increasing for the exothermic reaction. To really delve into lesson 12, students are now asked what math equation could help determine whether a chemical reaction is endo or exothermic. Most students will come up with at least one of these 3 possibilities. Let's check them out. The first equation focuses on what students can directly measure when they are observing a reaction, namely the final temperature when the reaction has completed compared to the initial temperature when the reaction was just about to start. If that temperature difference is positive, that indicates an exothermic reaction because the temperature of the surroundings increases. The second reaction focuses on the heat of the reaction by subtracting the potential energy of the reactants from the potential energy of the products. The heat of the reaction would reflect an exothermic reaction when the potential energy of the products is lower than the potential energy of the reactants, giving you a negative delta H. The reaction that lesson 12, however, focuses on is this third one. that emphasizes the bond energy of the reactants compared to the bond energy of the products. Notice that they are flipped compared to the previous mathematical equation. Strength of the reactants minus the strength of the products. Again, if the reaction is exothermic, that means the product bonds would be stronger, similar to the previous equation. That would result in a negative delta H. The lesson then provides students with a table, and the table shows them average bond energy in kilojoules per mole. I'm now going to show you the 3 key reactions that I chose for my students to analyze by making use of that average bond enthalpy table. The first reaction is very simple. We're breaking bonds between the hydrogen atoms and between the chlorine atoms to form new bonds. So we're starting with homonuclear diatomic molecules to form heteronuclear diatomic molecules. And you can decide what you would like your students to be able to do, whether it's balancing the equation, writing down word equations, showing the work for how to determine the heat of the reaction, and coming up with the final conclusion. Is the reaction exo or endothermic based on those bond energy values? The second reaction that I chose is the infamous Haber process, where hydrogen and nitrogen gas come together to form ammonia. And I'm making my students balance this reaction, writing the word equation, coming up with the work to determine the heat of the reaction based on the bond enthalpy or bond energy values, and then concluding whether the reaction is exo or endothermic. The final reaction that I have my students analyze involves the combustion of methane gas. And you can level this reaction up by having your students specify whether the molecules involved are either polar or nonpolar, and what intermolecular forces enable these molecules to interact with one another. Once the students have done those 3 reactions and their analyses, they are asked to create a final atomic model that represents this chemical bonding storyline. I do help my students out by giving them a starting point. They are then supposed to think about what should they include in this starting diagram. What words should they include? What other images should they include? What is important? What should be left out? And can they incorporate the key concepts that they've learned over these past 12 lessons? I'm showing you here my idea of what I would love my students to include. You're seeing here the exothermic version, highlighting that bonds are broken when a reaction starts, which is dependent on the bond energy, the bond enthalpy between the atoms involved. It shows you a transition state, and it shows you that in this particular case, stronger bonds are formed, indicative of the bicep curl, and the thicker arrow leaving the products. I also included the chemical potential energy diagram. Alternatively, students can simply flip that same reaction, and to emphasize the endothermic version traveling from the right to the left now requires a greater amount of energy to break the existing bonds, shown here on the right, and less energy is released when the weaker bonds are formed. So with that little bit of coaxing in the beginning, here are 3 models that my students came up with. And again, they could choose whether they wanted to do that in a digital form, for example, by using the drawing tool in Google Docs. Some students instead chose to use Canvas, and some students prefer to simply do it on paper, take a picture, and upload it to their digital lab document. And to really end this lesson, and this is often tough to do, you really have to take your students back to that driving question board, because that gives the students that final chance to look at what questions did we leave with during one of the previous lessons, and what questions do we still have. Let's go through these last 4 questions. Number 1, how does bond strength affect the change in temperature when reactants turn into products? They should be able to answer that question, but it's a good one to keep on our driving question board. If we had a set of reactant species, can you rearrange them into multiple different product substances? That's a good question. Let's think about that for the future. Third, how do endothermic and exothermic reactions compare to the strength of the bonds forming? This is another question that they should be able to answer at this point, but an important question to keep in mind. And lastly, how do you know which bonds are broken? How do you know whether ionic bonds or covalent bonds or intermolecular forces are broken? Or for that matter, metallic bonds, not shown in this question. So these are the 4 questions that we have kept as a class on our final driving question board. This concludes the 12th lesson of the chemical bonding storyline. The bonding storyline that is connected to the following 2 NGSS and NYSSLS standards, including matter and its interactions, and energy change in components of a system. All of these lessons, including the first 7 lessons of Part 1, as well as the last 5 lessons of Part 2, have been chronicled, and you can watch these again in the Stunning Storyline playlist. If you're interested in any of these storyline lessons, as well as my other mostly chemistry resources, go to the link in the video description below. In exchange for your email, you will receive a link to this Google Doc with all the lesson resources as well as the teacher keys. Thank you very much for watching. Bedankt voor het kijken. Tot ziens and see you in the next video.